Good morning everyone. So in this video I am going to explain about the discovery of subatomic particles. So what is a subatomic particle? Subatomic particle means when you divide the atom you will get some particles. They are called subatomic particles, or the particles which are present inside the atom is called subatomic particle. Okay, see, when you divide the atom. So according to modern theory, atoms can be divided. So when you divide the atom, so when you divide the atom, you will get the subatomic particles. Subatomic particles. Subatomic particles are these are also called fundamental particles. Fundamental particles. Okay, so what are the subatomic particles or fundamental particles here? Electron, proton, and neutron, etc. These are known as what? Subatomic particles. Apart from these electron, proton, and neutron, we are having positron, positron, positron. Okay, positron, pions, mesons, neutrino, and anti-neutron, anti-electron, anti-proton, etc. Many subatomic particles they have found in the atom. So here the main subatomic particles are electron, proton, and neutron. So these are the main subatomic particles. Okay. Now let us discuss about the discovery of these subatomic particles. So these subatomic particles are discovered by using the discharge ray tube. Okay. So this is the discharge ray tube. So who designed the discharge ray tube? So here the discharge ray tube is designed by William Crook. Okay, this is the discharge ray tube. It was designed by the scientist William Crook. William Crook has designed the discharge ray tube. Okay, so what is the structure of discharge ray tube? So discharge ray tube made up of a glass tube. It is made up of a glass tube which is having one opening here. From this opening, we can control the pressure inside the glass tube, and two electrodes are sealed in it. Sealed in it means two metallic plates are sealed in it. They are connected to a very high voltage source. Okay, so this is about the discharge ray tube. Discharge ray tube. Okay, so it is made up of a glass tube. It is made up of a glass. It is made up of a glass, and opening, it is having an opening. It is connected to vacuum pump, and two electrodes are sealed in it, and these electrodes are connected to a very high voltage source. Okay, so this is about the discharge ray tube. Okay, so discharge ray tube, discharge ray tube, it was designed by designed by scientist William Crook. William Crook, and so it is made up of with glass tube. It is made up, so made by glass tube. Okay, so it is having one opening. It is having one opening connected to vacuum pump, connected to vacuum pump. It is used to control the pressure inside the glass tube, and two electrodes are sealed in it. Two electrodes, two electrodes are sealed in it, sealed in it, which are connected to, which are connected to, which are connected to high voltage source, high voltage, high voltage source, high voltage source. So that is the simple structure of this discharge ray tube. So then what is the use of this discharge ray tube? So we will see what is the use of this discharge ray tube. So generally at normal conditions, at STP conditions, gases are act as insulators, which means gases cannot conduct electricity at normal conditions, like normal temperature, normal pressure, and at normal voltage. They are not at all going to conduct any electricity. But gases can act as conductors at such conditions. So like at very low pressure, at very low pressure, at very low pressure, say for example 10 power minus 2 atmosphere, 10 power minus 2 atmosphere, and at very high voltage, very high voltage, very high voltage difference, very high voltage difference, they act as gases, act as gases, act as electrical conductors, act as electrical conductors, gases act as electrical conductors. Okay, so these conditions we can achieve, these conditions we can achieve in the discharge ray tube. Okay, so at these conditions gases act as electrical conductors. Okay, so now let's see the once again this discharge ray tube. Okay, so this discharge ray tube. Now when you see the discharge ray tube, so here this is connected to a very high voltage source, and here vacuum pump is there. By using this vacuum pump, they can create this type of pressure, 10 to the power of minus 2 atmospheric pressure, very low pressure, and high voltage. They create a high voltage like this. Okay, high voltage by connecting to a very high voltage source, say for example 10,000 volts. So that what is happening here, gas is present inside this, it can conduct the electricity. So when you perform this experiment at these conditions, when you perform this experiment at these conditions, we can observe releasing of some invisible rays from the cathode, and they are traveling towards the anode. So the identity of this invisible rays by we can see by using a fluorescent screen. So here they use the some fluorescent screen which is made up of with zinc sulfide. Okay, it is made up of with zinc sulfide. So when these cathode rays, or when these invisible rays which are releasing from the cathode, when they touches to this zinc sulfide screen, this screen is going to give some glow. So it gives some glow. Okay, this screen will give some glow. So based on that glow, we can conclude that some rays are releasing from the cathode, and they are traveling towards the anode. So this experiment actually done by the William Crook. So when he do this experiment in this discharge ray tube, so what he observed, releasing of some invisible rays from the cathode, and they are traveling towards the anode, and they are touching, when they are touching to this zinc sulfide screen, they are going to give some glow. Okay, so now, so let us see. Okay, so let us consider. So this is the discharge ray tube. So rough diagram I am going to draw. This is the discharge ray tube. Okay, so now in this two metal plates are sealed in it. So one is connected to anode, another is connected to cathode. So here this is the negative terminal and this is the positive terminal, and that the electrode which is connected to negative terminal is known as, it is known as cathode, and the electrode which is connected to positive terminal is known as anode. Okay, so now here it is a very high voltage source. So for example 10,000 volts, and this is connected to vacuum pump. It is connected to vacuum pump. Okay, so here by using this vacuum pump we can create some pressure here, 10 to the power of minus 2 atmosphere. So at these conditions the gas can act as electrical conductor. So when you do this experiment, some invisible rays are releasing from the cathode and they are traveling towards the anode. Okay, so how we can say they are releasing from the cathode and they are traveling towards the anode? So here what he is doing, William Crook coated with the zinc sulfide screen. He is coated with the zinc sulfide screen. So let us consider this is the part zinc sulfide screen, ZNS zinc sulfide screen. Okay, so when these rays are going to hit this zinc sulfide screen, they will give some glow they are going to give. Okay, so based on this observation he concluded that some invisible rays are releasing from the cathode. So these rays are nothing but, these rays are known as what? Cathode rays. Cathode rays. So cathode rays are discovered by, these rays are discovered by William Crook. Okay. Next, let us see the properties of cathode rays. So what are the properties of cathode rays? Okay. Now let us go to the properties of, okay, properties of cathode rays. Okay, so cathode rays travel in straight line. So the properties of cathode rays was studied by the J.J. Thomson. Okay, J.J. Thomson has studied the properties of cathode rays. So he explained the properties of cathode rays. The first point what he observed, cathode rays are traveling straight line. Cathode rays are travel in straight line. Cathode rays are travel in the straight line. So how we can say the cathode rays are travel in straight line? See, so cathode rays are travel in straight line. How we are going to conclude they are going to travel in a straight line? Okay, so when you keep a metal object, in the path of cathode rays, what is happening here? So we can observe the image of this metal object which is placed in the path of cathode rays. So we can observe the image of this metal object on the zinc sulfide screen or fluorescent screen. Okay, based on this we can say the cathode rays are traveling in straight line. So in our general life also we observe the shadows or images. So how we can get the image or shadow? Due to the property of light. Light travels in a straight line. So when the light is traveling in a straight line, so when you keep any object in the path of the light, what happens? So you observe the shadow. This is the property of traveling in a straight line. Okay. So here also cathode rays are traveling in a straight line and they are forming an image. Okay. So based on this, we can conclude they are travels in the straight line. Okay. Next, cathode rays can rotate a light paddle wheel. Cathode rays can rotate the light paddle wheel which is placed in the path of the cathode rays can rotate a light paddle wheel. Okay. So how we can say the cathode see. So cathode rays are rotating a light paddle. This phenomenon we are going to observe. Okay. Cathode cathode rays cathode rays can rotate a light paddle wheel light paddle wheel which is placed in the path of the cathode rays. So why they can rotate a light paddle wheel means because they contain material particles. So they contain material particles. They contain material particles. Okay, means they have some particles in the cathode rays. Cathode rays contain some particles and they have kinetic energy also. They have what? Kinetic energy also. Next, so previously we know that cathode rays are traveling in a straight line, but when you place an electric field or a magnetic field, what is happening here? The cathode rays in the external electric field or external magnetic field, they are not traveling in the straight line. They are not traveling in the straight line. Okay, so here we know cathode how the cathode rays are going to travel. They travel in the straight line in the absence of external electric field as well as external magnetic field. But when you keep any external electric field, so here when you keep any external electric field, what is happening? Cathode rays are not traveling in a straight line. Instead of traveling in a straight line, they are traveling in a curved line. Means they are deflecting from their path. So means cathode rays are deflect from their path, the external electric field as well as in the external magnetic field. Okay. So here in the external electric field, they deflect towards the positive plate. They deflect towards the positive plate. Whereas in the external magnetic field, they deflect towards the north pole. Okay. So this is the property of negatively charged particles. First of all, they are interacting with the electric field and also magnetic field, means they are some charged particles. Okay, cathode rays are having some charged particles. Okay, cathode rays are having what? Some charged particles. Cathode rays have some charged particles. Some charged particles. So how we can say they are having some charged particles? Means because these are interacting with the electric and magnetic field. In presence of external electric field, they are moving towards the positive plate. In presence of external magnetic field, they are moving towards the negative pole. Means cathode rays are deflected by electric field, cathode rays are deflected by also magnetic field. This shows cathode rays are consist of charged particles. Okay. Next, and you observe, okay, right, okay. So cathode rays are having some charged particles. How we can say they deflect towards the positive pole and negative pole. Next, what we can say here, for so here what he concluded, J.J. Thomson concluded, cathode rays are nothing but cathode rays, cathode rays contain, cathode rays contain negatively, negatively charged particles, negatively charged particles. For these particles he named as negotron, negotron. So the name negotron is given by the J.J. Thomson, but the negotron again changed by the name electron is suggested by the G.J. Stoney. G.J. Stoney. Okay, G.J. Stoney has given the name electron. So these cathode rays contain some charged particles. Okay, and they have some kinetic energy. They can rotate the light paddle wheel, and they can interact with the electric field and magnetic field. So hence we can say that they are charged particles. And for these charged particles, J.J. Thomson given that is negotron, and the name electron is given by the G.J. Stoney. Okay, so these are the properties of the cathode rays, and finally cathode rays contain what? Negatively charged particles. They are called electrons. Okay. Next, let us see charge to mass ratio. Charge to mass ratio. Specific charge of electrons. Specific charge. Specific charge of electrons. Specific charge of electrons. So specific charge means charge to mass ratio. Charge to mass ratio is known as what? Specific charge. Okay. So this specific charge of electron is calculated by the scientist J.J. Thomson. J.J. Thomson calculated, J.J. Thomson calculated specific charge, specific charge, specific charge of electrons, specific charge of electrons by using modified discharge rate, by using modified discharge rate, modified discharge ray tube, by using modified discharge ray tube. Okay, so now let us see the what is the this modified discharge ray tube. Okay, so now we can see the modified discharge ray tube. So this is the modified discharge ray tube. So here same everything is arranged like discharge ray tube only, but here what is he done some modifications. So he made it is like a one curved glass here. Okay, and same one high voltage source he used. Two electrodes are sealed in it. One is connected to positive, one is connected to negative. So the one which is connected to negative is known as cathode. The one which is connected to positive is known as anode. So this cathode and this is anode, and he made a some small hole in the anode, and he performed this experiment. So when he performed this experiment, okay, so without any external electric field and magnetic field, So the cathode rays are used to travel in a straight line and they are going to hit the zinc sulfide screen here. Okay, and consider this is the point A, and he applied the electric field. When he apply the electric field, when he applies the electric field, what happens? They are not traveling in a straight line, they are traveling in a curved path. Okay, and when he apply magnetic field also, they are not traveling in a straight line, they are traveling in a curved path. Okay, so now let us see. Okay, so what is the modification he did in the discharge ray tube? So this is the modified discharge ray tube, and here he used a very high voltage source. So one is very high voltage source, and here he coated with the zinc sulfide screen. He coated with the zinc sulfide screen. Okay, this is the zinc sulfide screen. So in the absence of, when you do this experiment, so when you do this experiment in the absence of external any electric field and magnetic field, so these are going to travel in a straight line and they are going to hit at the point A, and when you do this experiment by using any external electric field, okay, so how they used to travel? They travel towards the positive plate. They travel towards the positive plate. Why? Because we know electrons are what? Negatively charged particles and hit at point B. And when they when you keep any external magnetic field, north pole and south pole, what is happening? They are traveling in a curved path again and they are touching at the point C. Okay, so now here we should understand the 3 points very clearly. So in the absence of external magnetic field and electric field, they used to travel and hits at the point A. When you apply only external electric field, they are deflecting from their path at touching at the point B. If you use only magnetic field, they are deflecting again touching at point C. And when we apply simultaneously, when electric and magnetic and magnetic field, when electric and magnetic field apply simultaneously, simultaneously means at the same time, simultaneously. Okay, simultaneously again, and by simultaneously and careful balance and careful balance careful balance between electric and magnetic field, magnetic magnetic field. Again they travel in straight line. Again, how they are traveling? In a straight line and hitting at point A. By observing all these phenomena, able to calculate the specific charge. And one more thing he is observed that, what he observed, the magnitude of deflection, the magnitude of deflection is directly proportional to charge. It's directly proportional to charge. Okay, so here charge increases, magnitude of deflection is also increases, and inversely proportional to the mass. If mass increases, magnitude of deflection is going to decrease, and is directly proportional to field strength. Field strength. Field strength, which means if you increase the more magnetism, means if you apply the more amount of magnetic field, they are going to deflect more, and if you use the more external electric field, more amount of external electric field, they are going to deflect more. Okay, so the magnitude of deflection depends on the charge on the particle. So here the charge on the particle increases, charge on this particle increases, magnitude of deflection is also going to increase, and mass increases, charge also, magnitude of deflection is also increases. Next, magnitude of deflection is directly proportional to field strength. Field strength in the sense magnetic field and electric field. Okay, this is the electric field and this is the magnetic field. If you increase the strength of this electric field, the deflection is also going to increase. If you increase the strength of magnetic field, the deflection is also going to increase. Okay, these are the phenomena he has observed in this discharge rate. Okay, and finally what he concluded, the E by M ratio, the E by M ratio of the E by M ratio or a specific charge, E by M ratio, E by M ratio, okay, the E by M ratio of cathode rays, cathode rays is constant. It is not depend on, it is not depend on the, it is not depend on the type of gas, it is not depends on the type of gas which we take, which we take in the discharge relative, which we take in the discharge relative, discharge relative. Okay, so, which means children, in the discharge relative you are going to take hydrogen gas or helium gas, hydrogen or helium, or you can take neon or oxygen, you can take nitrogen, whatever the gas you take, whatever the gas you take, all these are having etc, all these are having same E by M value, same E by same specific charge value. So the E by M value of electrons is 1.7588 into 10 to the power of 11 coulombs per kilograms. So or 1.7588 into 10 to the power of 8 coulombs per grams. Okay, so this is about the E by M ratio, E by M ratio of electrons. Okay, this E by M ratio of electrons is always, it is constant, it is always constant. Okay, it is not going to depend on the type of gas. Okay, right. This is about the discovery of electrons and their properties. Okay, in next video I will explain about the discovery of protons and their properties, discovery of neutrons. Okay, thank you for watching.